Today we're talking about square roots and imaginary numbers. And there's a reason why I'm bringing this in right now. We're talking square roots and imaginary numbers because when you have a graph and you have no roots and it's out here, it's because there's a square root that has a negative number in it. Okay, and we'll get to that, but I want to cover imaginary numbers before we go and talk about using the quadratic formula and looking at quadratic functions. But I just want to tell you that we're not doing something independent today. It's not, oh, this is kind of crazy idea and I'll just learn this for the quiz and then we'll be over with it. No, this will go throughout Algebra 2. This is just the beginning of it. I'm just teaching it in isolation, which I don't normally like to do. So that's what's coming. All right, radical review. Do this one quickly. 45 is 9 and 5. Perfect, because that's a square in there. That's 3 squared times 5, which is 3 root 5. What can I do with this one? You guys remember this from Algebra 1? Yeah? I could either simplify while it's underneath the square root, but oftentimes in Algebra 2 it's not going to be able to simplify. So the square root of 32 divided by 81 is equivalent to saying the square root of 32 divided by the square root of 81. So the square root, so we're going to treat them independently. So the square root of 32 is 16 times 2, and the square root of 81 is 9 squared. I'm going to skip this step since we did that one earlier. So this would just be 4 root 2 over 9. So if you need to write that down, go ahead. This is as far as we're going to take it in your homework tonight. What's coming is there's still a square root underneath here. Like, let's say, do you guys remember the rule about having square roots in the denominator? It's no bueno, right? It's called, so we have to multiply by root 3 over root 3. That's what's coming, but none of that in your homework tonight. Just as complicated as this here. So go ahead and copy that down real quick. Let's get to it. Keep an open mind, all right? So the square root of negative 27 is the square root of negative 1 times 9 times 3, which equals negative 1 times 3 squared times 3, which equals 3 square root negative 1 times 3. Now the reason I'm leaving this negative 1 is because this is what makes it imaginary. And I'm going to show you why it makes it imaginary. So when it's imaginary, I bring it out of the square root sign and I say 3i square root 3. Okay, so let me do a little box up here. If I were to use an area model and I were to say this is a box or square, square means all sides are the same, correct? So if this side is 3, what's this side? So what's the area of my box? 9. If I told you I had a box with an area of 16, what would each side be? How do you know? Because you just do? Because 4 times 4 is 16. Or the square root of 16 is 4. So couldn't I technically write it like this? Let's do a different one. The square root of 25 times the square root of 25. What's the area in here? 25. See how I did that? Take a second to absorb this. Aren't I just saying 5 times 5? You see it? So if you have 25, if you take the square root, so you see how they're inverses of each other? So the square, I mean physically if you look at it, the square is the area, the side is half of that, but in multiplication terms. So you're splitting it up in two. Here's another way you can write it. 25 to the 1/2. 25 to the 1/2. Did you know that you can write root 3 is the same thing as 3 to the 1/2? They are interchangeable. It is the same thing. But does it make sense why it's a half if you look at it like this? You're taking 25 and you're saying, well, one side of the box is here, one side of the box is here when I multiply them. So 25, we'll go even further. Take this right here and say 25 to the 1/2 times 25 to the 1/2. What's 25 to the 1/2 times 25 to the 1/2? When we multiply bases, we add exponents, right? So isn't that 25 to the 2 over 2, which is 25. All right. Now, this is how I teach my Algebra 1 students with boxes and area models so they understand what squares and square roots are. All right? So some of you haven't seen that before. But I think it's helpful when I do this to say, just like if I said, root 16 times root 16 is 16, correct? So couldn't I say root negative 27 times root negative 27 is negative 27? What's wrong with this? Why can't it be negative? Because no area is negative. Now, some of you want to say negative 27 times negative 27 is positive 27. It's not, right? If we're looking at an area model and you talk about conceptually what this means, I'm not multiplying them by each other. I'm saying together they are negative 27, the area. So since we can't have a negative as area, we call this guy right here imaginary. Okay? All right, so let's start talking about imaginary numbers. And I'll go further with this. Let's see. Yeah, I'm going to have to put it here. Okay, so I to the 0 is, what is, if something's to the 0 power, what is it always? No. Okay. To the 0 power is multiplication, right? We're going to make it even more visual. If I were to say 2 times 2 times 2, how is that represented? 2 to the 3rd. What if I don't have any 2's? What would I say about that? You can't say 2 if you have no 2's. It's not nothing.
Why is it not nothing?
Because there's always an invisible 1 in front of something. Isn't there? What property is that? Identity property. 1 times anything is always itself. 1 times 1 is itself. So there's always an invisible 1, just like when you're adding, there's always an invisible 0, if you'd like to say it that way, right? Okay? So for some of you that are only used to rules, this is going to be very difficult because it's making a different part of your brain think right now. Okay? But I'm trying to, you can follow all the rules you want, but I'm trying to make something stick. So anything to the 0 power, if you have no 2's, you don't have any 2's, right? But you do have a 1 in front of that. Okay? Let's go back. So I to the 0 power is, I to the first power is I squared. What? -1. This is y. Isn't -27 -1 times 27? Right? So if I were to use this model, isn't this really a -1 times 27 and a -1 times 27? So a -1 inside of here. What do I say when you have a -1 inside of here? We did it here. I take it out, and what do I make it? An I root 27, and make this one an I root 27. What's I times I? I squared, which makes -1. Let me give you a second. All right, so I'm going to move on to I cubed. What would I cubed be? It would be I squared times I. Well, what is I squared? -1, so it would be -I. Right? If I have an I squared, isn't that -1? So now I have -I again. I to the 4th is I squared times I squared. What's I squared? So isn't this -1 times -1, which is just 1. What's I to the 5th? It's I squared times, actually, isn't it I to the 4th times I? What's I to the 4th? There's lots of ways you could look at I to the 5th. You could use a whole bunch of these together, right? So I to the 4th is is 1. 1 times I is I. I to the 6th. -1. How do I know so quickly? -1, I, -1, -I. 1, I, -1. What's the next one going to be? -I. Misdirection. What's this one going to be? You should be able to look at it. How do I know it's -I? Follows the same pattern. Look, I'm just going backwards. So if this is -I, what's this one? -1, and what's this one? I, -1, -I. 1, I, -1, -I. 1, I, -1, -I. Okay. So I'm going to show you how to use these problems and be able to only use what's in blue right here. So this is all you have to memorize right here, what's in blue. And you really don't have to memorize it because anything to the 0 is 1. Anything to the first power is itself. We just went way over and over what I squared means, what I squared means. -1, and then the I cubed, if you can't remember which one it is, you've got a 1 and a -1, and an I, and now a negative I. There's a pattern. So is it really that much to memorize? If you understand it? No. The only one you really need to memorize is I squared. That's the only one you need to memorize. The other ones you can derive from knowing what you're doing. Okay, let's move on. So I want to know I to the 45th. Isn't what's I to the 4th? Let's look back. I to the 4th is 1. Because it's a full circle again, right? Times I to the 4th times I to the 4th. The reason I to the 4th is because if it's a cycle of 4s, right, I've got I to the 0, I to the 1, I to the 2, I to the 3. It's a cycle of 4 before it starts over again to I to the 4th, right? You guys see that? 1, 2, 3, 4. 4 divided by 4, I should say, how many 4s are in 4? Just the I with how many left over? None? Does that make sense? I to the 0 is still 1. Does that make sense to you guys? If I said I to the 6th, how many 4s are there in 6? 1 I with how many left over? That make sense? No? Okay. If I know I get I to the 4th, this is always going to be 1. So couldn't I say, instead of writing this all out, I to the 4th times I to the 4th times I to the 4th, how many I to the 4th am I going to write? Can you tell me? I'm going to write 44 of them before I get to 45. A lot. How many? How do we know 11? Because 11 times 4 is 44, right? Do I really want to write? Now, how do I do that? Didn't I just say 45 divided by 11? Sorry, 45 divided by 4. So 45 divided by 4 is 11 of them. How many do I have left over? Okay, are you following me? No. Let's figure this out. How much is I to the 4th? I'm going to write this out, just so we have it. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11. With how many left over? 1. This is a representation, or this is a representation. What is I to the 4th? 1 to the 11th times I to the 1. What's 1 to the 11th power? 1 times I to the 1? I. Write that down. 1. All right, let's try another one. You want to try this one on your own? Try it on your own. Okay, how many I to the 4th are there in 31? 7, because 7 times 4 is 28. So I'm actually going to write that. I to the 28 with how many left over? 3. I to the 28 is really I to the 4th how many times? 7. Oh, you guys already told me that. Right? Isn't this really just 1 7 times? Now I say to myself, okay, so I need my little table. I to the 0 is always 1. I to the 1 is always I. I squared is my magic one. -1, not magic, we figured out why, right, with an area model. And I cubed must be -I. So my answer is -I. Is it really that bad? No, it's 1 times itself 7 times, which is just 1. And I cubed is always -I. Yes, sir. Yes. Try another one? Okay. What about these? Oh my gosh, you guys are such whiners. It's not that bad. This says 3I or 3 times I. 3 times I times 4 times I is really 12I squared. What's I squared? -1. -12. Easy, right? What about this one? Try this on your own with a shoulder partner, please. Reporting. How many of you multiplied these together? Do you get the same answer? A negative times a negative is a positive. 20 is 4 times 5, and 12 is 4 times 3, which is 4 squared times, there's no squares in there, right? So I can multiply them by each other, which is 4 root 15. Let's see if that works. Let me do it the other way. This is really I times 4 times 5 times I times 4 times 3. Does everybody agree? Okay. So this is really I times 4 squared times 15. Everybody agree? So it's I squared times 4 root 15. Isn't I squared -1? Do you get the same answer? No. Why not? Why do you not get the same answer? This is wrong. Completely wrong. When you're using invisibles, when you're using a -1 inside of the square root, it's a negative. You have to consider the fact. So when you're multiplying them together, you can't ignore the negative because that's what made it imaginary to begin with. So if you multiply a negative times negative and make a positive and all pretty, you just completely eliminated the fact that it's an imaginary number. It's kind of like the same reason why we have to do the plus or minus in front of a square root. Because when you've got squares in there, when you're squaring stuff, you get rid of negatives, right? And when you have a negative to begin with and then you just decide to get rid of it, it's kind of underrepresenting it. It's gone. It disappears. And we can't let it disappear. because we know from the very beginning, from the get-go, that there was a negative in there. It's not going away. If I get rid of that negative and I'm talking roots, I just said my graph crosses the x-axis. When this tells me right away that it does not. So when you get rid of a negative underneath the square root, you completely change the function. Completely change it. Make sense? Why we can't get rid of it? Okay, let's go to our closing thought. All right, what does an imaginary number look like conceptually? What does it look like conceptually? Right? That's what it looks like conceptually. All right, on your assignment sheet, what is I to the 0? What is I to the 1? What is I squared? What is I cubed? That's what you need. Those are the tools right there. Good job, guys.